Hello students, and welcome to your lecture on vector analysis. We're going to talk about some theory and application within GIS in general, and then how that plays out within our ArcGIS software, which this semester is ArcPro. All right, moving right along. The primary vector analysis tools that you will run into in this class and then also in a lot of your GIS life are selection tools, proximity tools, map overlay tools, and then spatial join tools. Spatial join I'm going to actually save for the next module. Though it's a spatial tool, it also integrates quite nicely with our concept of working with tables and joining by that type of data. The selection tools I'm not going to go over specifically in class. I'm going to assume that you have a good wide use of select features, interactively selecting, select by attribute using the table to make your selections, and then also select by location, which is a tool that allows you to select in one data set and then ask the software to choose and find in other data sets places and features that overlap in those areas. So if you haven't had some experience with all three of those, I encourage you to go off and do that. They will come into play as soon as Lab 1. You'll need to be able to work with these tools. So go ahead and get out there and look at those. We will focus today first on our map overlay tools and then on our proximity analyses. The tools we will not cover in depth today are clip and erase, but I just want you to know that they are included in our map overlay or multiple input analyses. These are just your basic tools that take a cookie cutter shape, and clip cuts that shape out of your data set, and erase does exactly what it says. It erases that shape out of your data set. So really helpful, really nice tools. We will start our conversation with our other basic map overlay tools, which are merge and append, and then get into, after that, a conversation about those more advanced tools that do what we call geometric intersections. All right, so our basic map overlay tools that we're going to talk about today are merge and append. They can both be found under data management tools in general within Toolbox. Both tools combine both your geometry and your attributes from multiple data sets. So the big difference is that merge is going to take all of your inputs and create a brand new output. It's going to create a new data set. Append, however, is going to take all of those data sets. You're going to have to choose one as the primary data set to have everything else append to that data set. So your primary data set using that tool is going to be altered. So if you need to keep copies of all of your originals, merge is the way to go. But if you want to add data to an existing data set, append is the way to do that. Both of these tools make the assumption, geometry-wise, that you have no overlaps or no big gaps between them. So both of these screenshots show you combining, merging, appending two data sets that are either seamlessly next to each other in spatial location or have additional features that you'd like to add into an existing data set, but they nicely line up. If you do have data that has overlaps, either in lines or in polygons, what's going to happen is that these overlaps, the geometry is just going to float on top of each other. There's no way to isolate where that overlap is. So that's where we're going to talk about geometric intersection. If you want to be able to identify those areas of overlap, you will not want to rely upon merge and append because no geometry from any of your inputs is altered. It keeps the same geometry. When it comes to fields, you can tell it to keep all of your attribute information from all of your inputs. And if you really get in and work with the field map portion of these tools, you can really start to learn how to get your items and your fields in your table to, they can either kind of grow left to right, where you just tag on more fields for the additional data sets you merge and append, or if it's a data set that you know they all really share the same type of attributes, you can work with that field map to get those attributes to get stored into the proper field in your output data set so that your table doesn't get long and wieldy. So those two data sets I'm going to assume that you have some familiarity with. We will use merge in our exercise just so that we have a really hands-on example of the difference between merge and those geometric intersection tools. All right, that said, we are going to move on to our advanced map overlay tools, and those are those tools that do our geometric intersections. So you might be asking, what is a geometric intersection? Well, a geometric intersection is any area in your spatial data where from separate data sets that 2 points, 2 lines, or 2 polygons, actually really 2 or more, where they share space. That is the intersection. That's the intersection of their geometry. When it comes to tools that take advantage of this intersection, the geometric intersections can be used to identify the areas of shared space and the areas of non-shared space. So in our cute little example here, you're going to see these shapes moving on as we talk about these particular tools. We have purple polygons and a yellow polygon. Our yellow is this circle, the purple are these rectangles. If we were to combine these data sets using the intersect tool, you'd see here we'll end up with only that area where both of our input data sets existed, where they intersected. If we look at union, it's going to take where all of our data sets, the full suite of all of their features, it's going to retain all of those, but it's then also going to show us where they intersect geometrically. So the key here is that this intersection happens. These features are broken where they overlap. So in our intersect example, we end up with two kind of pie-shaped polygons. The great thing about these polygons is that they now store attributes from all of our original data sets that participated in that intersection. So you could click on this polygon and understand which purple polygon it belonged to and which yellow circle it belonged to. Down here on union, the same. You could identify which polygons existed only in the purple ones to begin with, or only in the yellow one to begin with, or where they were both overlapping. So these are the tools we're going to talk about, and we're going to talk about how features break where they overlap when we use these geometric intersection tools. These tools are how we start to identify shared space, and also how we can start to ask about changes over time. So the first tool we're going to talk about is the intersect tool. So we're going to kind of change our conversation and not talk about blue and purple polygons and yellow polygons. Let's talk about these in real world scenario terms. So let's pretend like our rectangles are parcels, and that circle there is the buffer of a fire hydrant. And this particular municipality is going through their annual hydrant flush, and they know that the hydrant flush will affect a particular perimeter around each of their hydrants, and they know that this is going to cause some localized flooding for some of our parcels. We could use the intersect tool to identify where these fire hydrant flushes and these parcels share space and create a data set of that. And that shared space then will have information in two polygons. This polygon here will tell us which parcel it belonged to and also which fire hydrant perimeter it belonged to, and so will the one next to it. So our feature, that intersect area, has been cut out from the overlap of both data sets, and it's been broken where they have a representation of being overlapping. All right, so that's how that plays out when it comes to polygons. You can also get creative with the intersect tool, and you can also intersect lines. But when you intersect lines, you ask for the output type of point, and it's going to give you from two line data sets the point of where those line data sets intersect, and also the XY coordinate for those intersections, and also all of the attributes from each of your input data sets. So my personal real life experience with this tool was that years ago, the Butler County Stream team came to me because they needed to have some XY locations of safe sampling spaces. So they didn't want to go onto private property where they knew that they could gain access to streams. They knew if they stayed along the road, they were on public property. So if there was any place where a road crossed a stream, either in a culvert or a bridge, they knew that they could drop a sampling bottle there. But they didn't know where all those were. And in the county and in most counties, there's not a comprehensive GIS database that represents all of those culverts and all of those bridges. That is starting to change as more data is being collected, but there's not GIS data on everything out there right now. So I was able to grab a data set of streams and grab the roads data set, put those into the intersect tool, and the output was a point data set that gave me the XY location of where they could go to, and also stored the information about the road that was participating in the intersect and the stream. So for their data collection, they always knew which road they were on and which stream they were on and where on that stream they were. So really great example. So you can think about this too if you're more interested in physical planning structures, maybe where do railroads and roads cross, or where are other path intersections, where is like the Oxford area trail, where does it intersect with all the roads throughout town, where might you have to put up signage or really be careful or adjust for your adjust speed limits and things of that nature. So that's how you would use that tool there. All right, moving on, if you were thinking about this and we were using the union tool, also doing geometric intersections, but instead of just choosing that area where they only overlap, where they intersect, this chooses the full suite of all of our input features from all of our input feature classes. So in our parcels and hydrant example here, the parcels and the hydrant all get saved, but where our hydrants are gets essentially burned into our parcels here. So you'll have polygons that you can identify and see that it only existed as a parcel, it's not being affected by your hydrant, or you can click on this area here and see, yes, it is affected by this particular hydrant and it's also part of this particular parcel. So you can see how things get combined, but where they are combining and overlapping, where those polygon boundaries are, they're breaking for the output data set and creating separate polygons, and that allows us to store attributes individually for these areas, specifically also store attributes for area. So we can now calculate area for each of these parcels to see how much of each of the parcels is affected by the hydrant flush in this example. All right, identity is a tool we're not going to use in class, but I like to show you that it exists. It uses the exact same logic as intersect and union. But identity gives you a little bit more control over your output shape. So with identity, you choose an input feature and an identity feature. And what happens is that the identity feature is effectively burned into the geometry of your input feature. So in this example here, you can see that the inputs were the parcels. That's what we wanted to keep. But we wanted to really break our parcels where we knew that that hydrant was going to be affecting us. But we didn't care about that little bottom moon part of our hydrant area that wasn't part of the parcels. So by choosing it as an identity feature, that geometric intersection happens only on the parcels data set. You could also flip the logic here and use the hydrant area as your input and the parcels as the identity. And your output would be the circle shape, right? It would be the circle of our hydrant area. It would be broken into 3 pie pieces, and you would be able to see from each of the individual pie pieces which ones were associated with parcels and which one wasn't, was having no impact on these areas of parcels. So identity, geometric intersection, same logic as union and intersect, you just are in more control of the shape of the output data set. All right, so that's talking through the actual tools themselves. Now we're going to talk this through in pictures so that we can see some examples. So this example here is going to be using a multi-ring buffer of from actually an old exercise I used to do in class, which was to model a train derailment in another part of the county that in Trenton. And we did a 1 mile and 5 mile buffer. So here's the view of the data, the geometry, and then also the attribute table. The other data set we had was a data set just of city limits. So these are not townships, not counties. This is just the incorporated actually city boundaries. And you can see here this part right here, this green one, that's the city of Trenton. And there's Middletown, and you have 7 Mile and Dartown, New Miami, Dartown's over here, 7 Mile, New Miami, Hamilton, and then Monroe in here if you're familiar with Butler County. So these are the 2 data sets. And these are the tables associated with the data sets. What if we wanted to ask, where does the buffered area overlap with the polygons? Where do we have an intersect between these 2? So if we do that, here's what that output looks like. You can see if we overlay these within a GIS, these are the polygons where they both exist. You can see the city of Trenton is actually bisected by those buffers. Part of it's within the 1 mile buffer, part of it's within the 5 mile buffer. You can see these cities on the edge get the rest of themselves cut off because those portions of the city are outside of this 5 mile buffer. So here's what the visual of that would look like. Here's what the table of our intersect data set looks like. So let's break this table down even further. So you can look at here, I've highlighted in green the fields that came from our buffer, FID and buffer, and then I've highlighted in red the fields that came from our city data set. Notice that for every record associated with each individual polygon in our intersect data set has information about the buffer polygon that it was part of and also the city polygon that it was part of. It is combined not only spatially but combined tabularly all of that information so that I can come click on any of these polygons now and know what portion of the buffer they were in and what city they originally belonged in. Now, one way we keep track of features always, but especially with these geometric intersection tools, is looking at those feature identifiers, those FIDs, or in the geodatabase model, the OIDs. So when we combine those, we really want to start paying attention to those FIDs. If we use the tool union or identity, we may have a situation where we end up with an FID value of -1. And an FID value of -1 means that that polygon didn't exist in all of the input data sets. It was missing from at least one of those input data sets. So when we are looking at a data set of intersect, we should not see any -1s, right? Because all of our output polygons are representations of areas that exist in all of our inputs. So all of our FID values across all of our table records should all be greater than or equal to 0. They should be a positive value, because there's no need for a placeholder saying, this area didn't exist in our buffer or didn't exist in our cities data set. But let's pretend, and this is the little reminder there, that area is in both data sets, meaning that the FID values will be a positive value. There's no need for that negative placeholder. But what if this had been a union? Let's pretend like these two data sets were combined, and this is what it looks like on the output. These all represent separate polygons. So you have this polygon in here, this polygon, this purple one has been split into 2, this pink one has been split into 2, so has the blue one, and then this area in here represents a polygon as well. So you can see that we have lots more polygons in this output data set than we did in the intersect data set. This is going to be a data set that has some FIDs of -1. For example, this particular area exists in both data sets. So you're going to have a positive value for both your city and your multi-ring buffer. However, this little pink area out here only exists in the cities. It didn't exist in the multi-ring buffer. So when you look at the table record for that polygon, it'll have information for the city, but not for the multi-ring buffer. And you'll notice that the FID value is going to be a -1. That tells you it was not in the buffer, but then you can look across and see that it was in the city data set. Same for this area in here. There's no cities there. So the city FID in the output table is going to be -1, but your multi-ring buffer FID will be a positive value, greater than or equal to 0. So we will play with this a lot in our exercise, but I really wanted to give you guys a visual of understanding those -1 values and how they play out with the table, of highlighting areas that weren't in one area, in one data set, but were in another. All right, so there is a disclaimer when it comes to all map overlay tools. And it is that area, perimeter, and length are not always updated in the output data set. Meaning that if you do a clip, the area or the length of that data set isn't updated. It still represents the value from the original larger data set, which you can imagine that might cause huge problems if you go to deliver that information to someone else who has to make a decision or has a policy based upon the numbers you're giving them. Now, this disclaimer is also different for our different GIS data models. This is actually true for shapefiles. Shapefiles, for whatever reason, the tools do not update area, perimeter, and length. However, in the geodatabase model, those values are updated. So you will notice as we move and migrate into the vector analysis portion of this class, we're going to move ourselves into the geodatabase model simply because we want that to happen for us by default, and we don't want to have to remember to do it all the time. There is a process and a workflow if you're working with shapefiles that after you run these tools, you just automatically go back to area, perimeter, or length, and right-click on those fields and calculate their geometry. And that just runs a little script that goes in and recalculates the area, the perimeter, or the length of that particular data set for all of its features. But this is really important. And I will show you and highlight this for you as we move throughout the semester, and also give you ways to do this for shapefiles. We won't be doing it in class all the time, but I'll make sure you have the documentation so that you could do it on your own. All right, next up are proximity tools. And these are just the tools that you can use to evaluate one data set based upon its spatial location to another data set. The one tool we're going to start off with is one that it's really basic, but it actually can solve a lot of interesting problems. It lives under generalization. It's called Dissolve. This is the tool that actually, when we talk about the buffer tool, we can see how it plays out being actually run within another tool. But just to run the Dissolve by itself, it's going to look at your data, You're going to tell it a field that's within that field you have multiple records that share a common value. And it's going to look at those features that are adjacent to one another that share that common value, and it's going to dissolve the boundaries between them. So my first real use of this when I came to Ohio was that I was looking around for basic Ohio data. I could find a state boundary from one place, a data set of counties from another, but I learned real quick when I was trying to make maps of anything where you had to show that Ohio River southern boundary from both of those data sets, that the boundary just didn't overlap. Like we highlighted in the data types lecture, where you're dealing with data from different sources of different scales that have different numbers of vertices and different detail along some of those natural based political boundaries. So my solution was I had a data set of counties. It had a field in there that had a state name. And if all of my counties are in Ohio, they should all have the name Ohio in the state field. So I could run it through the dissolve tool and say dissolve based upon the field of state. Every county that was adjacent to one another that had the same value, the boundaries between those features dissolved. So what you ended up with was an outer boundary of the state of Ohio. So that was a really nice use of the tool to give me a really basic data set that I could use for some nicer mapping. You can see over on the right hand side here too is another example. So if we had a data set that had lots of polygons, but several of them represented water here in the blue, several that represented maybe grasslands here, and then several of them represented wetlands over here. We didn't need all of these subdivisions. Maybe these were different types of water, different types of grass, different vegetation within the wetland. We just wanted an overall look of those three main vegetation types or land cover types. If the polygons stored a field that had a common information, so if it just had land cover type, and those three polygons had water, 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 grassland, 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 and then also wetland and wetland, we could dissolve using that field any of the polygons that are adjacent to each other that share that information. The boundary there is going to dissolve, and we're going to end up with these three primary polygons that are showing us just water, grassland, and then wetland. So that's dissolve. It's a nice tool to know, and I like to introduce it because it does come into play when you use the buffer tool, which is the next one we're going to talk about. So the buffer tool is a basic tool that takes your inputs, they can be point, lines, or polygons, and it creates a buffer polygon around your input features, and you get to say what the distance is going to be. If you're working with lines, you get to decide what the end shape of that buffer is going to be. Is it going to be squared off? Is it going to be rounded? And it's that dissolve type in there that gives us control over if we end up with overlapping buffers. How does the tool deal with that? Do we just get overlapping polygons, or can we kind of manage for those to take care of those overlapping boundaries? And you'll notice for all of the different buffer tools, there is a method option. And if you look at this, you're going to see planar and you're going to see geodesic. For areas that you're working on that are smaller in area, so finer in scale, so county level, state level, maybe region level, the planar is fine. It's relying on your spatial reference, your projection, and it's going to measure in distances there, straight line as the crow flies. If you're dealing with data that is a large region-wide or countrywide or worldwide, you want to toggle down and use the geodesic method. And all that's doing is the geodesic method is incorporating the curvature of the Earth effectively into that tool as well. So if you're really going over large distances, you really want to make sure that you're accounting for the differences that happen over space with that particular model. But for most of the things that we will do for class, we will always keep the method as planar. And honestly, the reason why it's the default is you'll notice that a lot of the Esri tools already have an option filled out for a lot of the parameters. And that's actually kind of smart, because what they do is they populate those with the parameter that's most often used in that tool. So if you kind of just want to speculate with a tool, try a tool out first, leave all the defaults and see what happens, and then go back and read the help documentation. And just know that what was filled out by default was what usually gets done by most people when they're running the tools. All right, let's walk through buffer, which hopefully you guys have already done, but we're really going to talk about that dissolve option and what that means for our geometry and our tables. So if we have these 4 points and we run a 300 foot buffer around them. Our output, if we leave the dissolve type to be no dissolve, is up here in the upper right. We end up with 4 disks, 4 buffers, and where they overlap in space, you have overlapping features. So this would be looking, if you were to look at them from a side profile, you'd see them basically sitting on top of each other. You could pick them up individually. If you were to toggle this dissolve type to say dissolve all into a single feature class, you're going to end up with a look like this. Any place you have overlapping buffer polygons, the interior boundaries there are going to be dissolved, and it's just going to capture the outline of where they all were. So a much different geometric look. And as we're going to see next, it also plays out with big differences in your tables. So this is what the data set and the table looks like when you choose that no dissolve option. You end up just with your 4 disks that are overlapping. Notice when you choose this option, your buffer table retains all of the original attribute information of your point data set or your line or your polygon, whatever it was you were buffering, it copies the attribute table, which is really nice. And then at the very end of the table, it adds a field called buff dist, which tells you the distance. Now you have to remember the units that you chose, but it's going to tell you the numeric value of that particular buffer distance. So a lot of really rich information in that attribute table. Every buffered polygon, every disk, and every buffer that you have is going to have its own individual table record. So 4 polygons, 4 table records. Now, notice how this is different when we use the dissolve all into a single feature class. So we don't have the individual polygons. It looks, if we were to look at the map, like we have 2 polygons. But when you open up the table, you only have 1, and that is this into a single feature class. So all of our polygons, whether they overlap or not and are dissolved in the middle, they're all going to be collapsed down to a single table record. And that creates what we call a multi-part feature. A multi-part feature is simply where you have multiple features, multiple parts that share a single table record. So instead of that traditional one-to-one record of one geometric feature to one table record, you can have multiple geometries associated with a single table record. Now, you might ask, why does this ever happen? Well, these types of data sets were built to be able to exist because, number 1, they can reduce the file size, and number 2, they can help with some data organization. If multiple polygons really just need to have the exact same information, you can do that by creating a multi-part feature. More often than not, though, we really want to retain that 1-to-1 ratio of 1 feature per 1 table record. So there is an extra step that you can do with these types of data to actually split those polygons apart. But before we get there, I want to talk about that last option you'll notice in the dissolve tool, which is what I've boiled down to is dissolve based upon fields. So this is where you get to choose individual fields, one or many, in your data set to say and what you're saying is if in the table multiple records share the same value of the dissolve field that I'm choosing, dissolve all of those features, all of their buffer polygons into a single table record. So you can see the output here by choosing this PW type, which if you look in here, 2 of our records are a W fire hydrant and 2 of our records are an A fire hydrant. The output is 2 of our polygons here have been dissolved together and 2 seem to be standing alone. So we can reason that these 2 are either W or A, but they're both the same because that boundary between them has been dissolved. So let's look to see what that looks like with this data sets table. Now, we have 3 polygons, but we don't have 3 table records. We still only have 2 because what it's done, it's dissolved your features into records based upon the field that you chose. So you only have 1 record representing all A fire hydrants and 1 record representing all W fire hydrants. So you still have a multi-part feature. You just have one of these has 1 polygon and one of these has 2 polygons associated with it. And notice when we use any type of dissolve, we lose all of the tabular information from our input data set, which is fine, and there are times when that's okay, but you just need to be aware of what's happening when you choose these different options because they do play out both with the geometry and with the attributes that you have. So you might be asking, okay, this is great, but how do you fix this? If I have multiple polygons, I want to be able to have multiple records because that's where I'm going to see the area. That's where I might be able to do another select by location. I want to be able to isolate those units. So you can do that. It's just in the Edit tab. There's on the feature subgroup, the modify button will open up a list of modify tools, and under divide, you'll see the explode tool. And when that opens up, you then in there use this select tool within explode to select, draw a box around your feature, and it will tell you how many multi-part features you have, and then you'll have the option then to run the tool in order to split all those apart and give them all their own table record. So let's see what that looks like with this original dissolved one where we chose the dissolve all. And you look at the old table. This was our multi-part feature, one table record, multiple polygons. We use the explode tool, and then the output of that is that we have a table record for each individual polygon. Now, it doesn't give us back any other additional information. We don't have any of the original information from our fire hydrants here, whether they're an A or a W. We don't have the buffer distance, but we do at least have an individual table record for each of those polygons if you were to need it. All right, so the last thing about buffer we're going to talk about is the tool multi-ring buffer. So if you have a scenario where you need to represent multiple distance away from a feature, you don't have to run buffer multiple times. There's a tool built for that. And what it does is it goes and creates rings, essentially donut rings, around your input feature at specified distances. So the nice thing also about lines is that you can choose to do multi-ring buffers or individual buffers on either the right, the left, or both sides of those lines. So if you need multiple distances, multi-ring buffer is the one that you want to pay attention to, and notice that it also has all of those same dissolve options that are going to play out just the same way as with their regular buffer tool. All right, the last tool we're going to talk about is this near tool. So this is one that doesn't get used very often, but you will occasionally get a very simple question that you want to say yes to. But then you have to think hard about what tool would I use to do that. So let's say a friend came to you and was like, hey, I know you know this GIS stuff. I have a data set of sampling sites and a data set of roads. I need to know what road is closest to each of my sampling sites. And you're like, yes, I know GIS can do that because I know where your sampling sites are. I know where the roads are. There has to be a tool that can measure that for me and systematically give me out a table, as opposed to me going to every sampling site and measuring manually to all of the individual roads. The answer to the tool there, to your question there, is the proximity tool, NEAR. So what NEAR does is you have an input feature, and in our example here, that would be your sampling sites. And the NEAR tool asks you to identify a NEAR feature, which is what data set do you want to know the distance to? So in our example, that would be the roads. The output is going to add on fields to your input. So it's going to add on fields to my sampling sites. It's going to tell me two pieces of information. Number one, the attribute of the nearest road feature. And number two, the distance, the straight line or Euclidean distance to that feature. Now that distance is going to be in the units of your coordinate system for the input. So the units of my sampling site projection are going to be the units that distance is reported in. So you have to understand your data, again, whenever you use analysis tools. So you want to make sure all inputs are in the same coordinate system. So this would have been a question you answered way before in your workflow. So you would be very aware of your data. But you do need to know that there's nothing else telling you what those units are. It is just what the units of the projection was for the data set when it was put through the tool. So if you run this tool and then reproject the data, the output from that NEAR tool will not update. You'd have to rerun the NEAR tool or do a conversion of your own to get the new distance. So a really powerful tool that answers a really basic question that we don't use all that often, but when we need it, wow, it really is the workhorse to answer some really simple questions for us. All right, what's up next is an exercise to put into practice a lot of what we've just talked through here, particularly paying attention to the geometric intersections. And then in lab 1, you'll get to play with the concepts of buffers. So after you get done with this, take a break and get ready to move on to the Missouri River exercise.